resistance, reactance, and impedance. You've likely encountered these terms before, but do you truly understand their significance? Let's unravel the mysteries behind these concepts. When we apply a voltage difference across a conductor connected to a light bulb using any kind of power supply, the light bulb will turn on. Let's represent the voltages at the two ends of the circuit using a scale like this. When the voltage is equal on both sides, A and B, the light will not turn on because no current flows. Let's set the A end to 0 volts and increase the voltage at the B end. If the voltage at B exceeds that of A, current will flow from B to A. Conversely, if the voltage at B drops below that of A, current will flow from A to B. When the voltage difference between A and B remains constant, we call it direct current. When the voltage varies, and current changes in magnitude and direction frequently, we refer to it as alternating current. To gain a better understanding of these two types of currents, we can graph voltage and current. In DC circuits, voltage remains constant, resulting in a constant current. To simplify, we'll overlay both charts. In AC circuits, voltage varies in a sine wave pattern, causing the current to follow the same pattern. Again, for clarity, we'll overlay both charts. Having a solid grasp of these two types of currents is essential as we move forward. This is a current conducting wire. For example, let's assume it conducts the alternating current. When we connect electronic components to this current-carrying wire, they have the power to influence and modify the behavior of the current. In a DC circuit, each component connected to the current path impedes the movement of electrons, resulting in a decrease in current flow. This phenomenon also occurs in AC circuits. A component can hinder electron flow, causing a reduction in current, much like in a DC circuit. However, it's important to note that in AC circuits, current typically follows the voltage, increasing and decreasing in sync with it. But that's not the sole way current behavior changes in AC circuits. As voltage changes, some components resist the change, causing the current to not strictly follow voltage fluctuations. Conversely, others accelerate the current changes, further complicating the relationship between voltage and current in AC circuits. We have now discussed three types of current changes in a circuit, and these changes depend on whether the type of current flowing through the circuit is AC or DC. The first type involves simply decreasing the magnitude of current, and it can be observed in both DC and AC circuits. In this scenario, current and voltage changes occur simultaneously. The second type entails current changes occurring after some time following a voltage change. This phenomenon is unique to AC circuits since in DC circuits, voltage remains constant. The third type involves current changing before a voltage change, and it is also exclusive to AC systems. We say the first type of current change to the resistance of a component. The second and third types of changes occur due to the reactance of the components. More specifically, inductive reactance causes the current to lag behind the voltage, while capacitive reactance causes the current to lead the voltage. Now let's discuss resistance and reactance. To gain a better understanding of these concepts, we need to explore the behavior of resistors, inductors, and capacitors. Let's try to grasp these concepts using a water analogy. Here we have two pistons, each half filled with water, and both connected using a water pipe. If we apply a constant pushing force to piston A, the water will begin to flow from piston A to piston B. This happens because the applied force increases the water pressure in piston A, prompting the water to move from the high-pressure region to the low-pressure region. The same phenomenon occurs in an electric circuit. A battery has two terminals, positive and negative. The positive terminal has a high potential, while the negative terminal has a low potential. When we connect these two terminals using a conductor wire, a current begins to flow from the positive side to the negative side. Let's return to the water piston example. If we modify the applied force, the water flow will also change accordingly. We can represent the applied force and the water flow in graphs. When the pushing force decreases, the water flow from A to B also decreases. If we apply a pulling force to the piston, it can be represented in the graph as a negative force, resulting in water flowing from B to A. To provide a clearer perspective, let's combine these two graphs like this. This water analogy serves as an analogy for AC circuits. Now, let's examine the impact on water flow when different types of components are connected to the water path. Here's our setup. We are applying a constant force to piston A, resulting in a steady water flow in the pipe. Now, what happens if we connect a narrow nozzle to the water pipe? It's quite straightforward. If the force remains the same as before, the narrow nozzle decreases the water flow in the pipe. Whether the force remains stable or changes direction, the reduction in water flow is noticeable in both scenarios. The same principle applies to an electrical circuit when we connect a resistor. The resistor diminishes the current flow through it. As we mentioned at the beginning of this video, resistance opposes the flow of current and is present in both AC and DC circuits. Here we have a water wheel connected to the water pipe, blocking the water's path. To initiate water flow, the wheel must begin to rotate. Let's illustrate this with a graph of the applied force and water flow. Initially, there is no force on the piston, resulting in no current flow through the pipe. When we suddenly increase the force on the piston, the water flow cannot immediately increase. It needs to set the wheel in motion first. Consequently, the wheel starts to rotate, gradually increasing the water flow. After a while, it reaches a constant speed. If we abruptly stop the force while the wheel is still turning, the wheel will attempt to maintain its rotation, causing the water flow to persist for a moment before gradually decreasing and eventually coming to a halt due to friction within the pipe. This behavior arises from the inertia of the water wheel, which strives to maintain a constant rotational speed. From this, we observe some interesting characteristics. The water wheel delays the increase in water flow. The water wheel delays the decrease in water flow. When the force remains constant, the water wheel does not impact water flow, behaving like an ordinary pipe. When the force changes continuously, the water flow only responds after a delay. In general terms, we can say the water wheel resists abrupt changes in water flow. If the water flow is steady, the water wheel does not interfere with it. However, if the water flow attempts to change, the water wheel delays this change. This behavior parallels that of an inductor in an electrical circuit. In the case of direct current, DC, where voltage remains constant, the inductor does not influence the current. However, in alternating current AC circuits, where voltage is always leading the current, this effect becomes evident. This phenomenon is known as inductive reactance. As we mentioned earlier in this video, inductive reactance does not like to change the current through it. Also, it is not observed in DC circuits because current remains constant. Here we have an elastic chamber connected to the water pipe, serving as a barrier between both sides. Water inside A cannot move to side B and vice versa. We'll color the water inside B using green dye. The colored water cannot mix with the water inside A due to the membrane's impermeability. However, since it's an elastic membrane, it can expand to a certain extent based on the water pressure difference between the two sides. When we apply a pushing force to piston A, the membrane expands as shown. However, the water flow stops when the opposing elastic force equals the applied force. We can graph the applied force and water flow like this. When the applied force is constant, no water flows through the pipe. But when the force changes, we observe water flowing through the pipe like this. It appears that the water flow must change before the force changes. In general terms, we can say that the elastic membrane tends to influence water flow changes to delay force changes. In this example, the water flow is leading the voltage. If the force remains constant, no water flows through the pipe. However, if the force changes, the water flow leads the force. This behavior closely mirrors how a capacitor operates in an electrical circuit. In direct current, where the voltage is constant, the capacitor does not allow current to pass through. But in alternating current, current consistently leads voltage. This phenomenon is referred to as capacitive reactance. As we mentioned at the beginning of this video, capacitive reactance is not observed when the voltage remains stable. Since current does not change in DC circuits, capacitive reactance is not evident in DC circuits. Now that we understand how different types of components affect the current in a circuit, the three primary factors influencing current are resistance, inductive reactance, and capacitive reactance. Resistance consistently decreases the current and is observable in both AC and DC circuits. Inductive reactance causes the current in a circuit to lag behind the voltage, and it's exclusively observable in AC circuits. Conversely, capacitive reactance makes the current lead the voltage, and it too can only be observed in AC circuits. The cumulative effect of these factors is referred to as impedance. In simple terms, impedance of a component signifies how it modifies the current within a circuit. That's all for today. If you think my contents are valuable to the world, you are welcome to join my Patreon community. Like and subscribe to Professor Mad for more interesting videos.